Ural University is somewhere in Siberia. They'll talk about the convert channels through the cache channels of HTTP protocol. Okay, it sounds great. So what the report is going to be about? So we need to find out what is that. First of all, what is the convert channel? Is any way of communication through any mechanism which was not intended for that. Convert channels are timing channels and memory channel. So memory is the channel which uses memory, and the convert timing is when we get certain regular behavior of a system and we transmit our information there. Also in the heading there was the HTTP protocol, of course, covered channels. It's more interesting for us to realize through the network. The two hosts participated. HTTP is one of the most used network protocols. That's why it's interesting to find covered channels there. That's why also we found the figure that an average covered channels in HTTP should give about 2 bits per second passing capacity. That's why it would be interesting to check whether it is true or not. Also, if we search for something that in HTTP, we'll find these channels on the lower levels, like IP, TCP. So, we found out what are the covered channels, why they are needed. They are needed to pass through something. They could be some commands, controls, like zombies and botnet, or in zombie browsers. If you talk about Beef framework, could be cryptographic keys or key exchange, or they could be used to transfer any illegal content. So now, in the cache headers, there are two of them: modified attack and request headers. Why we need them? If we have a large page with a big picture, every time we update the page, we don't want to upload the page again. That's why we can use the cache channel headers. Well, we also use such ideas like client-server channels. This is passive things, and they don't do anything. Client is more active. They send requests, and the server can respond. That's why covered channels from client to server are easier to implement if client wants to. The server needs to interpret it somehow. And from server to client, channels are more complicated, and most of them timing channels, so it's more interesting to research. So in order not to be that blank, let us, for example, get that. If range request header looks like the following request. Take the header, you tag. You cannot see that well with the pointer. It's classical part of attack. Header, and then we get information, and we write it. Then we have the client quickly sends a request, and the server gets information. So then, last modified response header is allocated with the red. Contains data of the last change. In that readable format, it tag, if it's more complicated, contains more information. It contains descriptor of this document, the size, and time. More precise format. They work something like that. Client is asking, has the page changed? The server says, yes, okay, go ahead. Or 3 or 4 didn't change. And the second headers. You have the same version as previous or not. And the server says either no, yeah. Okay, we have got the basic ideas, and that's the basic scheme. We see what needs to be done to implement our cover channels. Looks scary, but it's very simple. One side we have, I think it's useless thing. If we take a look from your side, from your left, hidden message that we want to send, we have two processes. Attacker 1, Attacker 2. Attacker 1 wants to send some information through message to Attacker 2. That's why they use a page HTML, which is stored at the web server in the middle. This red dotted line is the trust border with the internet. Everything's very simple. To send information, they use the page in the middle. What's important to observe, we have two scenarios where we can realize our hidden channel, convert channel. First, minimal requirements. We have this file with the secret message. All attacker 1 should do is read this convert information and change time of last access to a page. And attacker 2 must just have access to page to see whether it was changed or not. Second scenario, so-called full control over web server. Of course, there could be requests less strong, but for simplicity's sake, let us consider a situation when the attacker fully controls web server and gets some bonuses out of it in the future implementation, realization. What's proposed? Let's cover channel scheme. Attacker 2 has a HTTP request to that page that is used. Using the cache headers, understands whether it was changed recently or not. And then makes up the mind whether what bit was received. And remember that I have many cache headers, and we can separate all the covered channels into two groups, last modified based on UTAG based. Everything fits the channel scheme which I mentioned. The only different thing is that we're using different things to identify whether the page has changed or not. If the channel is clean, we see the header, otherwise we look at the HTTP code status. Okay, everything's simple. Need to realize and see what's in reality. Maybe it's pure theory, nothing works. So far, we have come across the classical problems for the covered channels on time. The only interesting thing we can say is that the classic covered channels network by time use special package called end of frame, which allow to synchronize the writing and reading processes. We managed to deal without them, not reducing the passing capacity of the covered channels through the passing of these packages, but use a combination of dynamic negative sleep combination. The process makes a request and see, oh, I could have slept for 2 seconds, I've slept 1.5, so that's why we have high synchronicity reached. So let's start chronological order. First experiment, last modified channel. Let's remember, it stores time with the precision up to 1 second. That's why passing capacity is just 1 bit or half a bit a second. It's not impressive speed. What the columns mean: sleep time, min start sequence, average sequence, max sequence, speed, accuracy. Well, without any error. Minimal 100% guaranteed size of information without the distortion. As we can see, it's enough for cryptographic key. We can use it also not speedy, precision or accuracy column, percentage of bits sent to the total percentage of bits sent. Okay, it's not impressive. Let's take a look at ETAG. It's similar, but ETAG stores time in different format with the precision up to microsecond. That's why theoretically we can get passing capacities of a channel up to 10.6 bits per second. Normally we get 1 bit. R1 plus R2 seconds. R1 is the time when attacker 1 gets the server, and R2 same for attacker 2. Well, speed is not impressive again because the speed of updating the cache headers by default on average is half a second, 1 second. In order for us to use it more effectively, we need to have quicker updated cache channel. We need to think which server needs better accuracy. Of course, file hosting. We started to think about file hostings, and we have seen that many file hostings like Google Drive or Dropbox and others have their own API. Using that, we can change files or get information about them, etc. That's why we can get that API. Have two processors of attackers get files to Google Drive and through that realize hidden channel described above. We can do that in reality. We see two links in the slide. Post updates gets the file's last access time. Now the speed is much better. We can do something about it, and we use Google Drive, which is very safe. Everybody trusts that, and we see in the table again the speeds and the precision and accuracy for different types of cryptographic keys. So I've seen the first scenario what we've got hidden channel which is anonymous. Looking from any angle we can find out about attacker 1 or attacker 2. They may not know anything about each other, which is very important. Core channel doesn't change HTTP request structure. How the request looks like. Any user would be the same. We use the functionality web standard. What's important? No web server modification. Everything works out of the box. It looks like a scoreboard or somebody often updates the page. And before we get to second context, the headers, which are based on if modified, looks like they will work even if the server obviously does not set e-tag or if e-tags are disabled. The server would respond with the status code 304, 200 or set, whatever. Second scenario, second security context. We got rid of that bad synchronization which took so many efforts. We can wait for a HTTP request and apply respectively. Then the passing capacity goes up. We get each bit for every request. And okay, we have realized that we got virtual and digital ocean, DC LAN, got the following dimension. Then now we can use local network. Time looks great then, and on internet 5 bits per second, it's much better than what we have seen in the very beginning, about like 2 bits per second. So great. What we have in the second scenario, we have again covered channel on the HTTP header, which doesn't change the structure. It will look very logical, and again it looks like something it's updating the page, and it's easy to realize and implement, and it's much quicker. Where we can use that and where we are using that, we have realized that with the beef module. Wanted to see how our cover channel works. Beef is a framework to test from the client side when we use it for web browser for JavaScript code. So what we have faced, lag of any synchronization functions and HTTP protocol, we had to find out. We couldn't do that for the first model rather than through the Google Drive, the first scenario. Same problems here again. It's easier to resolve when we control the web server, nothing extraordinary here. It's easier for us to get synchronized, easier to find out messages, and average is better. Okay, beef. You know that there they have extension there, module of extension, what is working on the server side, modules which are on the client side. That's why we realize the extension, which is written in Ruby, which has a couple pages to beef, and then module on JavaScript that is possible for receiving information. That's the data we've got. The speed is delighting, especially with the delay between this beef server and the infected browser. Results comparable server client DNS similar 5 bits per second internet, then bits per second local network. Proof of concept, as I said. So there's a video how it works. You can see it and watch on YouTube. So overall summary we found, investigated previously and documented covered time and channel-based and HTTP cache headers. We have made it most efficient in tag-based covered channels and browser exploration framework. B for covered communications, and also we implemented anonymously. Well, that's it. So thank you very much. Do you have any questions? Colleagues, use the mic. Hello. We have realized coverage channels in case it's any boutique from the controlled network, the bot from controlled network. This is easier to identify. Have you thought about it? So we haven't got this problem specifically. To any protection method, we can invent bypass method. We can think of any function which would calculate the sleep interval for the client and for the reading and writing process. Thank you. Those understand. What about the duplex exchange? We can use two channels, one-sided channels, like from server get information the way that on the server tunnel information, French headers, so everything is very realistic. No problem. Yeah. If there are no more questions, then thank you very much for your attention.